I'm now sending propositions to all of you. If Adolfo starts, if you have a little chance to read your email, you will see it.
Mag er staan. Zitten. Openen.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Adolfo Chaves-Jiménez. De verdediging zal in het Engels worden gevoerd. Okay, given the online setting, I assume that the candidate is ready. There's no Catherine. Welcome. A warm welcome for all of you at this public defense by the candidate of the dissertation entitled On the Coupling of Orbit and Attitude Determination of Satellite Formations from Atmospheric Drag. The Board of Doctorates of the TU Delft has installed a committee to evaluate the thesis and the propositions. The committee will have a debate with the candidate in public, and it is an honor to present the members for this committee to whom I extend a very warm welcome. Let me introduce all the committee members to you. Online, Professor Zhu from York University, Canada. Welcome. Then Professor Graman, University of Beira, Interior, Portugal. Also a warm welcome. Professor Lavanga, Politecnico di Milano, Italy. And then Professor Blom from TU Delft. Professor Vermeersen from TU Delft. And the co-promoter, Dr. Gu. And finally, here on the table, Professor Eberhard, who is the promoter of the candidate. Thank you all for taking part in this academic ceremony. My name is Professor van Keulen from the Faculty of Mechanical Engineering, and it is a pleasure to chair this session on behalf of the Rector Magnificus. I would like to start the opposition, and I would like to give the floor to Professor Zhu. Professor Zhu, could you be so kind to start the opposition and your debate with the candidate?
Okay. I suppose to. Mynheer the Rector, thank you for giving me the opportunity to ask the question. When the promo vendors, it's a pleasure to read your thesis. You have done a great job. I really appreciate the thesis. It's well written, but because of the duty as a committee members, I will challenge you some of the questions. First of all, I like the way you presented it. It's a research question. You put two big research questions for your thesis. But I also want to say the methodology, the subject you mentioned in your thesis, it seems quite common in the field. And the observers, observabilities, estimators, they all have been done. So my question is, what's new in your thesis? What's the innovation part of your thesis?
Hogeler de Opponente, thank you for your question. I really appreciate that this is the first question for my thesis because it allows me to clarify what is new. Definitely, the estimation method is quite common, is quite known, which is the extended camel filter. And the observability gremium is not new. It's actually very well known in the systems community, control systems community. What is new here is the actual consideration of the coupling in estimation. This is actually very normal for control theory, and it has been considered in some control settings. Actually, in Canada, in the University of Toronto, they use the coupling between orbit and attitude dynamics to control two satellites in orbit by the difference of the area of the spacecraft. But in estimation, it hasn't been used as long as we know. It hasn't been used. This consideration hasn't been used to improve the estimation of relative dynamics of spacecraft. We found out actually that in 1982, this consideration was done for a very, very large spacecraft by an author called Chaves in Canada, actually, also, with a spacecraft as big as the International Space Station. But for smaller spacecraft and relative dynamics, the consideration of coupling between orbit and attitude dynamics hasn't been considered to improve the estimation of the relative dynamics of spacecraft, the relative pose of a spacecraft. So this is important. When we use the observability gradient, what we wanted to do is to evaluate observability without depending on how good the estimator is. And the reason, because you're asking me that too, the reason why we're using a common estimator is actually to make it as clear as possible for the whole community. Because, you know, if we use a newer estimator, it wouldn't give the message, in an easier way for the whole community that actually the coupling improves the estimation. So first, we use observability to be independent from the estimation method. And from there on, we use this common estimator, I will say maybe the most common estimator for this kind of scenarios, to prove that this is the case. So in essence, the innovation here is definitely not the estimator, is definitely not the use of the observability gradient, but actually the dynamic model of the system that we're working on. I hope I answer your question properly. But if it is not clear, please ask me what I can clarify.
Thank you. Don't worry, I have following questions for you.
Okay.
Yeah. The next one I want to ask is in the section 4.4, you're talking about the verification. You want to compare the analytically derived derivatives and verified with by the numerical simulation. So my question here, are you doing verification to verify your result? Or are you basically just validate the result using an independent approach?
Hogeler, the opponent, thank you for your question. Let me rephrase your question. Are you asking if I verify the analytical results of the partial derivatives of the state in my system with another, if I verify it in some way, numerical or otherwise?
Oh, yeah, I want to say, because it's verification, the question is here. It's the verification of validation.
Well, Hogeler, the opponent, what I do is I work with a numerically graphic every single partial derivative that I have here. This is also very important. The part, because I know this question will come up because many people work on linearization, and because they work on linearization, I know they're going to ask, what's the point that I'm using for the linearization? Actually, when I'm doing the linearization, I'm doing the propagation of the complete orbit and attitude dynamics, and I use this trajectory to do the partial derivative of the system. So when I was doing the simulations, when I was working on these kind of things, I was doing the partial derivatives in one block, and the other part, I had the numerical derivative of these partial derivatives. So the verification was each one of them, I verified that they were as close as possible with a reference that I don't remember right now what was the difference, but it was in the numerical error difference, maybe something 10 to the power of minus 14 or things like that. But yeah, my verification was numerical, was graphical, just watching for 5 orbits or one orbit, 2 orbits, 5 orbits, if the result was the same.
So my question actually is not ask you what you actually did. It's because in the space industry, we have verification and the validation process. They are two different things.
Okay.
I'm asking you in what you did is the verification or validation. But you make it very clear you want to validate your result is correct. It's not to verify your code is doing it is supposed to do. Am I correct?
You are Hogeler, the opponent. You are absolutely right.
Okay, that thing I want to you after make a change to the proposition to that point.
Okay.
Okay.
Thank you. I really appreciate your observation.
Yeah. So my next question is more specific. It's the in the very beginning, like page 37 in your thesis, you said the J2 effect is negligible, so it's not considered in the current study. And somehow on the page 65, and you gave the discussion about the J2 effect. So
Yes.
I want to clarify, in your study, do you really use J2 or you just not considered?
Hogeler, the opponent. Thank you for your question. Actually, it allows me to verify and talk about the scenario that I'm using. The fact, and actually the title says I'm using atmospheric drag as the source of coupling. The reason why I'm mentioning J2 from the very beginning, and actually mentioning J2, and I say it very clear on the thesis, I use J2 as a matter of completeness. I actually talk about J2 and I actually talk about solar pressure, because anyone who actually could see the thesis could take all my results and could take directly the equations to develop more advanced models. Let's say somebody wants to do the exact same study that I'm doing, but they're working about geostationary orbits, then they can go for solar pressure. If they want to do any inclination orbit, they can use the J2 equations there. It's a matter of completeness. But my scenario is two spacecraft that are separated 1,000 kilometers, and the way, in order for J2 not to be influencing the results that I have, I'm working with an equatorial orbit. So the complete answer is no, I'm not using J2 because I'm working on equatorial orbit, so the effects is negligible, but I write the equations in order to have a complete thesis, and that it becomes, say, a document that can be used by anybody else that is working on a different scenario. And actually, this allows me to talk a lot. This allows me to talk and be very clear about the fact that my idea is that this tool that I'm creating, this set of tools, I would say it's a set of tools that I'm creating, is useful for any researcher who wants to take into account coupling without simplifications in any kind of a scenario, not only low Earth orbit. The low Earth orbit is just my scenario, but you could do whatever other scenario, even interplanetary, if you're talking about solar pressure, or geostationary solar pressure, or any other magnetical effects if you're taking them into account in some way. But yeah, I'm not taking into account J2.
Okay.
So, Professor Zhu, are you satisfied with these answers?
Yes.
Thank you very much. Then I would like to give the floor to Professor Guerman. You have to unmute. Yes, now we can hear you.
Well, first of all, I would like to thank the University of Delft and Menhir Director for inviting me, and congratulate the candidate, Vada Promovendus, and to greet all my colleagues that are present here, though probably in a distant manner. I would like to comment on your thesis, that it was an interesting read, and I enjoyed very much reading it. And before I start my questions about the content of your thesis, I would like to ask, or probably ask you to clarify your opinion about the proposition 10, which states that...
Sorry for interrupting you. Waarde candidate, can you please read proposition number 10?
Okay.
Of course, my pleasure.
And then we will hear the question from Professor Guerman. Please go ahead.
Proposition number 10. Achieving a perfect PhD thesis will demand an infinite amount of time.
Professor Guerman, now we would like to hear your opinion or question.
Well, as any optimization statement, whether it is true or not depends on criteria of optimality that you use. I would like to know what criteria do you use for quality of PhD thesis?
Hogler, the opponent, thank you very much for your question. I really, really appreciate that you talk about this proposition. Perfect. It's a matter of no errors, no deviations, no possible. When we talk about estimation, we always say this is close enough. This is close to the matter of 10 to the minus of 14, 10 to the minus of 16, 10 to the minus of 25 nanometers, or whatever other measure you're talking about. When I'm actually also a lecturer, and I teach control, and I teach system analysis. When I teach system analysis, the first class that I talk about, I always say, you know, we learn Newtonian mechanics, but then we realize Newtonian mechanics are not perfect in the case of very high velocities. When we are close to light velocity, then Newtonian mechanics are not perfect. So you might say Newtonian mechanics are a theory that are good enough, but they don't apply to every single case. So when I talk about perfect, it's something that cannot be challenged in any scenario whatsoever. When I talk about the thesis that is perfect, that is not perfect, we always joke about saying, well, a perfect thesis is a done thesis, right? And that's another criteria. But I definitely talk about the fact that, for example, and I don't know if confessing this is good in a defense, but I was reading my thesis yesterday and I found an error. I'm not going to tell you what the error is, of course, but I found one, right? I found something that is actually very difficult to find, but because, you know, I work on years on that, I would say, yeah, this is really important. And for example, I was discussing one of the members of this committee, and we found out that a bold variable, it was not supposed to be bold, and is written like this in a journal paper. In a journal paper, you expect that these kind of things are completely right, but none of us found that. And then these kind of errors, they still come and come and come. And when I said that, I said it from my heart, writing my thesis, saying I'm trying to do this as good as possible. But if I completely desperate, then it would take me an infinite amount of time to find all the errors, find everything that is possible. So that's what I really do.
Mm-hmm. I believe we can help you with this a little bit. Okay. But Waarde promovendus, could you clarify in a very brief way, why did you consider the formation flying where two satellites fly apart 1,000 kilometers while all the examples that you stated before, it talk about close formations, and 1,000 kilometers is not close at all.
Hogler, the opponent. Thank you very much for your question. Actually, it is deliberate. The fact that the Closey-Wittscheid equations are valid for very close formation make me think about a formation that is not close enough so that these equations are not as valid as they would be if the formation will be 500 meters or even closer references. I took as a reference, if I remember right, and I don't want to be completely, I don't want to say this is the case because it is not on the top of my mind. But if I remember properly, this is based on the Prisma mission, which I use in this case, and probably Professor Gill knows this by heart, but I don't recall if that was the reference that I used. But the reason why I use 1,000 kilometers is to make it clear that my equations are of general use. You don't have to restrict yourself to very close formations. Even though I don't use any inclination, you don't have to restrict yourself to any inclination. And even though I use a circular orbit, you don't have to restrict yourself to circular orbit. This could be elliptic, it could be highly elliptic, and it could be applied to any of the formations that right now are trying to do laser communications between satellites. So that's the reason I tried to make it far enough that it proves that it's valid for cases that are not close.
Okay.
I hope with that I answer your question.
Okay. Vārdi promovendus, could you please clarify us why in section 6 you consider on the direct measurements of all positions and quaternions and all data that you need, while in the previous chapter you clearly state, and I agree with you, that this is not the most interesting case. Most interesting case would be to measure only part of this data.
Hogler, the opponent, thank you for your question. Actually, I make it. I talk about this in chapter 5. Let me ask you to clarify this. Are you talking about chapter 5, where I use the observability gradient?
No, chapter 6. We are talking about your analysis of chapter 6 when you use for your Kalman filter construction the case which is labeled before as the least interesting in the previous chapter.
Yeah, it is. Hogler, the opponent, thank you for your clarification. The reason why I do this is because I want to focus on the effect of the dynamics themselves, not on the configuration of the not on the sensing methodology configuration. Actually, and I mentioned this on chapter 1 and briefly on chapter 2, mostly the improvements that I referred to, or the kind of improvements done in say extended Kalman filter of these kind of methods, they are done by improving the sensing methodology. So say you're using vision navigation or any other complex kind of system for the measurement, or taking the measurement in a different place of the spacecraft, or using more or less measurements to see how they work. The fact is that in my thesis, I don't focus on the measurement scenario, and I don't want the measurement scenario to intervene. So I make it as simple as possible so that for anyone applying my methodology, my scenario, they focus on the sophisticated dynamics method. So the sophistication, I focus on the dynamics method, and everything else besides the dynamics system, I mean, the engineering model that I'm using on the standard Kalman filter, is as simple as possible, so they can be developed quickly. Because, and this is something that we could do in the future, we could use another estimation method to make it to show that this estimation method with the coupled estimator works better than the extended Kamel filter, and that some measurement will work better with the coupling system than this simplified case. But yeah, this is the reason. It's just, you know, like we do in science, we try to focus on the effect itself, which in my case is dynamics, the astrodynamics in this case, orbit and attitude dynamics, absolute and relative, and everything else that is not related to my study is done as simple as possible. Somehow, in order to isolate what my study subject. I hope with this I answered the question.
Okay.
Professor Graham, in the interest of time, I would like to thank you and would like to ask you, are you satisfied with these answers?
Yes, I am.
Thank you very much. Then I would like to give the floor to Professor Lavanga, please. I think something goes wrong.
Oh, yeah, no, that's okay. Sorry, it took a bit of time to unmute.
Okay.
So, good morning. As the other colleagues of mine, I'm really glad to be here, and I congratulate for your thesis, and I enjoy with you with this really important moment and step in your life. So, main director, I would like to address proposition 7 and 8 to the candidate.
So, waarde candidate, could you please read for us propositions 7 and 8?
Meneer Director, should I read them both at the same time?
Oh, yeah, you have to read them both because they will both be discussed. Yep.
Meneer Director, thank you very much. Proposition number 6. The amount of missions with satellites.
Sorry for interrupting.
Yes.
7 and 8.
Sorry. Okay. Thank you, Meneer Director.
No problem.
Proposition number 7. Every single country in the world uses space technology. This is the reason why every single country needs to have space systems engineers. Proposition number 8. Developed and developing countries are able to work as equal partners in space missions.
Professor Lavanga, so please continue your opposition now.
Thank you, main director, and thank you, candidate. I would like to hear from you about those two propositions in terms of your position with respect to cooperations and collaboration in space domains, of course, among countries from an international point of view. So I would like you to extend the more concepts that are behind, because those two propositions can be read differently. So I'm curious about your idea and your feeling behind those.
Hogelerde opponent, thank you very much for your question. You don't know how much I appreciate the fact that you focus on this kind of matters. After I came back from the Netherlands, and this is the reason from this, it has to do with a personal story. After I came back from the Netherlands, I was part of the group that created the first Costa Rican satellite. The reason why we created the first Costa Rican satellite is because we believe that space technology could be used as a tool of development in my country. My country, being a developing country, is relatively developed from the educational point of view. So we cannot compete with other nations in a matter of cost. We have to compete in a matter of quality. And that's the reason why, for example, space technology, it's one of the areas where we could use our knowledge in software, in mechanics, in electronics, and everything else that we already have if we use space technology. So the fact is that I repeat this all the time, and I actually was able, I'm very lucky to repeat this in the United Nations. Every single country, even the poorest country, use space technology. I always say there are two kinds of countries: the countries who create the space technology and the countries who buy the space technology. It is very clear which countries are the most developed. And our idea, at least in Costa Rica, is to become part of the second group, to be able to create our own space technology. Why? I mean, maybe we can buy it and it's more efficient. Because every single country or every single group, they work their space technology focus on their own interests. So, for example, if Costa Rica is part of a mission with, say, space debris with Italy, because we're very concerned about the environmental issues, then if we propose, if we are part of, say, the control team or the estimation team that is creating the estimator for the satellites, then we're able to be part of the decision making. And we're able to focus not only on the interest of any country who is working on the space technology, but we also influence this kind of interest. So in this matter, we actually created a space system technology laboratory, and our focus is not to repeat what every other country did. I mean, to follow the path of the United States, which is clearly not comparable, but not to follow the path of the Netherlands, but actually to follow a different path, to actually study what are the capabilities of our own countries to develop space technology and what are the competitive advantages that we could use. Say, for example, Costa Rica is the most biodiverse country per area in the world. So now that we're trying to find plants that are feasible, suitable for lunar exploration or Mars or interplanetary, we could be the best place to be because we have experts on biology, technology. And I always say to people, if we find out what we are best at, then we don't have the fact that all our best researchers go to one country and don't come back, but actually the researchers come to Costa Rica because this is the best place to do this kind of research. So why we need the space engineers? To take advantage of our competitive advantages and actually be part of the use of technology and not only buying it, because in that matter, we're even more efficient from the economical point of view, because as I said, every single country uses the space technology. And not only, and this is very important, and I must say, and I must admit, this is very personal. I don't believe in the approach of developing countries, asking developed countries, please help me, please give me resources, give me money. But actually, I believe the way of a developing country to become a developed country is to focus your philosophy in actually act as equals. So if I say, I want to, our laboratory would like to cooperate with Politecnico di Milano, then we will tell you, well, we are experts in these areas and we believe we can do this and you do this. And then we share these decisions as partners. We actually have we have this kind of cooperation with the university, with George Washington University in the United States, where they are developing a CubeSat, a 3-unit CubeSat, that is testing a new propulsion system. And we in Costa Rica are developing ground sensors for monitoring of wetlands in Costa Rica. And we are developing the control system of this satellite, because we are telling the other groups that we are experts in the development of algorithms for control systems. So that's the way that we, in a practical matter, show that we want to work as equals in this kind of space project. So we developed the first satellite, we proved that we were able to, but from there on, we are working with other countries because Costa Rica is too small to develop complete space missions, but working from the expertise point of view as equals to be in joint space exploration, space missions. And actually, because we are as equals, then we are part of the decision making. And this mission, even though it's a mission with George Washington University, is focusing on the wetlands in Costa Rica. So we are creating a benefit for Costa Rica at the lowest cost possible, because they are paying everything and we are only giving, well, not only, because it's actually very expensive, but what we are giving this group is our expertise. And this I call one very good step to work as equals. I don't know if with this I clarify the question.
Definitely, thank you. It was a really complete answer.
So, in respect of time, you already indicated that you appreciated this answer, and I would like to thank you for your questions, and I would like to go to Professor Blom and to hear his opposition. Professor Blom?
Yes, I've just switched the voice. Waarde promovendus, I like very much to read your PhD thesis on a topic which is not familiar to me. The control theory and the filtering, that's familiar to me, but not your specific application. So that's really nice. And also you really did your best to show some things in very nice pictures. If you take, for example, the covariance matrix in the colors, I think that's a really nice job. I've never seen it before that someone did that in that way. So, but let's go to the specific question. And there I'm asking that question being known about what is happening in the normal atmosphere, but not what is happening in the space atmosphere. If you look at your results on page 110, that's your figure 6.6.
Should I show it here?
Maybe it's good to show it. I
Yes.
think all my colleagues will
Of course.
know this one. It's always helpful to see the picture.
Yeah, is page, which page is it?
It's page 110.
Okay.
One further.
Yeah. Here you are.
Yes, that's the one. So you show very well that your results are that there is a significant difference at 300 kilometer height, and that slowly diminish. So if you are above 700 kilometer, you have no gain anymore. And you did this for a setting of 1,000 kilometers apart between the spacecraft. Now the important question is that if you are at the Earth, around the Earth in normal airspace, then the density of the air will depend not only of the height, but also of the temperature, all kind of effects on the Earth. That means that if you are at different places, then the air density can vary even when you're at the same height. So I assume that a similar kind of thing will happen in space. How exactly, I have no idea. I never looked at it, but I assume you know. So can you please explain what happens when you have differences in air density, even when you're at the same height? And what's the effect on your method, in particular, when you increase the distance between the spacecraft? Now you have 1,000 kilometers. I think you didn't take into account this possible differences in air density, but maybe it already can play an effect. And of course, if you increase it, it maybe have a large effect. So can you please explain us about this?
Hogler, the opponent, thank you for your question. It actually allows me to mention something that has been my...
Can I ask you to throw out the picture so we see you? Is it possible?
Yes, of course. Okay, I think I tried
Yeah,
already.
it's fine again. It's fine again. Yeah. So you
Okay,
can
let's
answer
go.
the question.
Thank you very much for your question. Actually, it allows me to elaborate on something that has been an idea that I had, and I mentioned it on the conclusions of my thesis, and I mentioned at least a couple of times to Professor Gill. Yes, the fact, you're absolutely right. I am assuming that, and I mentioned this, I am assuming that we know the atmospheric density and that this corresponds to the solar maximum. This means that the amount of energy that we're getting from the sun is the maximum possible. Actually, if we are in a minimum, depending on the altitude, the density decreases at least 1 degree or 2 degrees of magnitude. So these effects, this graphic that you see is in a solar maximum. It really depends on how the sun is influencing the atmosphere. And if we get more energy from the sun than the atmosphere, there are more particles in the lower orbit. So that's the effect. The most important effect in the case of space is the solar effect, the solar maximum or the solar minimum. Of course, there are the differences. Of course, this difference happens in space. And actually, that allows me to elaborate one of the ways that I think that this research could go further in the matter of, and I think I mentioned this on the conclusions. If we work with different CubeSat configurations, then the density, the atmospheric density, could become a state for the estimation. So we don't assume that actually we are estimating the density itself, but we know it is unknown, and then we create a satellite that help us, depending on even the geometry itself, know which is this density, and actually using my method and actually my mathematical model to improve the estimation by taking into account this. I even thought, and this is really a crazy thought. I mean, it's not something that I have developed a lot, but actually we have thought of something like this. Imagine a scenario where we launch a CubeSat from the International Space Station. And this is something that the group of astrodynamics in the 5th floor could be very interested. And this satellite doesn't have active control, so that it stops, going round and round in order. It doesn't stabilize itself, but actually, it just goes round in a way that the geometry makes that this movement depends on the atmospheric density. So the rotation velocity, I mean, if you somehow, in a geometrical way that I couldn't show with my hands, and unfortunately I don't have a graphic like this because I haven't developed it as good as possible, but actually create a geometry, a deliberated geometry of a satellite that makes the satellite rotate so that we do the estimation of the atmospheric density. So this model will not only work to estimate the states themselves, maybe say we have very good sensing technology to estimate the states, but actually to estimate the density. That could help with analysis of space climate or things like that. And actually that's very inspired on aeronautics. So I think in my case, I would like to learn quite a lot about aeronautics. My background is electronic engineering, but I've learned a lot relatively from mechanics, and I would like to learn these kind of things to see how to optimize this and take that into account. Take that into account and actually make the estimation of the density itself. I think we can prove this even for simulators, and that would be very interesting. And I haven't seen anybody doing this in space. I remember, and I mentioned this at the very beginning of the opposition, that in Canada, and actually I think this is done by Planet. It's not called Planet Labs anymore. It's just called Planet. That they
may I ask you, because it's very interesting you explain this the future possibilities, but I want to like to go back to the question I have, and that is, if I interpret your explanation, it means that maybe your results that you now show for the 1,000 kilometer distance, that even when in reality this differences in air density at 1,000 kilometer may be so high that maybe even your results don't apply in reality. They apply in your computer simulations, in your computer model, but maybe not in reality. Is that correct?
Well, so why the candidates? Sorry for interrupting you. We already talked about optimization, and I give you a constraint here. Your answer can only last 1 minute.
Okay, thank you. Managing Director, thank you very much. Hogeler, the opponent. Actually, the main fact that differences the density is altitude. So the difference in 1,000 kilometers, I wouldn't know. I have to be honest. I don't know the answer. But if I have to guess, and I could research on this, if I had to guess, because the fact is the atmospheric density depends mainly on altitude, it wouldn't make that much of a difference in this case. So this result should be valid. But to make them valid, I have thought about working with data from current satellites and check this out, but it hasn't been part of my thesis results.
Yeah. Okay, thank you very much.
Thank you very much.
Professor Blom, I hope you are satisfied with these answers.
Yes.
Thank you very much. Then the floor is for Professor Vermeersen, please.
Dank u, meneer de rector, waarde promovendus. I also read your thesis with great interest, but of course I do have some questions. And let me actually follow up on one of the questions that Professor Blom posed to you on the effect of the atmosphere. In your outlook, you write that the present work may be further improved by using more advanced models of the variation of the atmospheric density. Now, this is a very general statement, and I would like to hear from you what is the most important aspect that you would like to see improved. Is it spatial variability? Is it temporal variability? Is it average, the outliers? What especially in these atmospheric density models would you like to see improved for your work?
Hogeler, the opponent, thank you for your question. Actually, the next step of improvement is even more simple than what you mentioned. The next step of improvement is actually working with high elliptic orbits. And in that sense, taking into account the variation of density will be the step. Just that, just the fact that the density varies with different altitudes, because even though I'm working with 5 orbits, and 5 orbits under the effect of perturbations become non-circular, they're almost perfectly circular. So every single scenario that I work on is assuming one single density, non-changing density. But it doesn't mean I don't take into account the variation of density. If you see chapter 4, where I do the linearization of dynamics, every single linearization of dynamics takes into account that the density depends on the altitude itself. And that's the only variation I take into account, density varying with respect to the altitude. So next step is even more simple, is the change of density with respect to altitude. And that sense, I already, with some of my students here in Costa Rica, we already developed this method, and I don't recall what's the method that we are using. It's in one of the manuals by NASA from a long time ago. And we can change from higher solar activity to lower solar activity and check both things for highly elliptical orbits. And that's the next step. What other next step we could work on? Actually, my idea, and this was not possible during the duration of my research, was to go to the 5th floor and talk to you and see what would be interesting for your group, because I know your group are experts on this matter. And after working with elliptical orbits, that was the way I wanted to go. I wanted to approach it, the group experts, I think Elko Dombors and these people, and ask them what would be the next step from there. But unfortunately, in this specific research, I didn't go to the next simple step.
Okay, thank you very much. Meneer Director, is there time for a small question?
Yes, you still have time. Yeah, please go ahead.
Thank you. So I've understood from your thesis that you have applied your models and your methods to CubeSats. I'm also very interested in, for instance, solar sails. So let's imagine that you're not dealing with CubeSats, but with solar sails. Would anything change in your methods, your way that you do your assumptions, or whatever?
Hogeler, the opponent, thank you very much for your question. It actually reminds me, it gets me back to what I mentioned at the beginning of the opposition. The fact is that this modeling works for solar pressure, and the solar pressure model is mentioned on the thesis. There wouldn't be any change. The equations are the same because I don't make any simplifications. There are no simplifications for non-elliptical orbits. There are no simplifications for anything else. I use the known linear equations for everything that I do. Even for the linearization, the generalization is applied to everything. The only thing that you will have to change is the fact that you are using the solar pressure as a perturbation effect. And you could say, with my model, you could use J2, you could use the atmospheric drag, but if you are too far away, maybe atmospheric drag, say for 1,000 kilometers, about 1,000 kilometers from the surface of the Earth. And then you take the solar pressure effect. And the other thing that you will have to change, of course, is the model of the spacecraft. But the good part is that the area to mass ratio will rise a lot because, of course, solar sails are very, they have a specific area, effective area that is very large, but the mass is very low. So actually the effect on the pressure itself will be very high. So to elaborate on this, to answer your question, the equations are the same. The only thing that changes is the perturbation, and the perturbation is already mentioned in the thesis. So you could, I mean, if we sit down with the MATLAB system, we could have it working in this afternoon, in Delft time, of course, and showing what happens.
Okay, thank you very much.
Thank you very much, Professor Van Meersen. So I would like to give the floor to the co-promoter, Dr. Gill. Please, the floor is yours. We cannot hear you.
Took some time to unmute.
Yes, now we can hear you.
Yeah. Thank you, my dear director. My question, my dear Promenders, my question is about your proposition number 6.
Waarde promovendus, can you please read proposition number 6?
Meneer Director, yes, thank you very much. Proposition number 6. The amount of missions with satellites information flying is going to increase each year.
Dr. Gill, please continue.
Yeah. Okay. So we know in the past that, especially around several years ago, that formation flying was a very popular topic, both for space missions and for research. Then in recent years, we see a big explosion of mega constellations. So constellations are now very popular in real missions. Then, relatively, the formation flying, we only observed limited number of real formation flying missions. So how would you justify your statement that that for each year the number of the missions of satellite formation flying is increasing?
Segeler, the promoter, Thank you very much for your question. Actually, that allows me to talk about the scenario that I'm working on. First of all, formation flying missions make some other missions that were only possible with single satellites possible in a cheaper way. And actually, now that we're working with private companies are trying to optimize the design of missions from the point of view of from the financial point of view. Then, for example, if you talk about mega constellations, it really depends on your concept of formation flying, because it really depends on what you classify as formation flying and what wouldn't you classify as formation flying. Because, for example, Starlink, the constellation by SpaceX, they have to do very, very precise estimation and control of systems to actually point one laser from one satellite to the next one. So it's really a kind of a conceptual concept, but I will have to say that really sounds like formation flying in some way. That's one example, but let me work in an example that is even more clear. In my scenario, I assume that the chief spacecraft has all the sensing technology, meaning that it has the technology to know the absolute dynamics, and it has the technology to know the relative dynamics of the second spacecraft. My scenario is completely related to only a single spacecraft knowing all the information. So the other spacecraft, the deputy, could be space debris. And we know space debris is probably one of the hottest topics in space. And it's very, very important, because if we as space engineers don't work on space debris, then we will not be able to work in space in very few years. Actually, I saw the TED talk by Professor Lavagna talking about this subject. And I think even though maybe this year this didn't happen in a relative way, this is going to be increasing and increasing and increasing. And I'm not even talking only about Earth. For example, I remember the CubeSat that was sent to Mars, Marco. I believe these kind of interplanetary missions will benefit from formation flying, even from fractionated spacecraft, a subject that you know a lot about.
But the candidate, could you try to finish your answer in a few seconds?
Yes, I believe from the point of view of growing, you will see what also happens in electronics. You will see that it keeps growing and growing and growing, because it makes missions cheaper and more efficient. And now the financing are important. I believe this is going to happen.
Thank you very much. Then we still have a few seconds to hear the most burning question from the promoter. Professor Gill.
Hartlich bedankt, mein Herr Direktor, Vade Promovendus. I have a question on precise orbit determination. You used in your thesis a simple orbit and measurement model, both for the dynamics as well as for the estimation, with typically 8 vector components of just a few scalar elements. Now, in real space missions, especially when you are dealing with precise orbit determination, your state vector often can comprise thousands of components, like, for example, small empirical velocity increments to account for atmospheric drag. My question is, would, in such a case, your research still be relevant? That means improve the orbit determination accuracy.
Geachte Promotor, thank you for your question. Yes, I believe it will be. Why? Because we are taking into account an effect that was not taken typically into account. So even though we have thousands of different vectors that we're taking into account, what we are accounting for is dynamic forces. So these kind of dynamic forces, they create an effect on the system itself. And if we don't take them into account, then it will happen what happens For example, in chapter 6, when we were working with the extended Kalman filter, and I actually use noise to model the dynamic effect. So if you use any other information to model the dynamic.
Ora est.
Thank you, Madam Beal. The committee will now withdraw for further deliberation in the committee room. This session is adjourned.